2000 Canadian Open Mathematics Challenge, Part B. Triangle ABC has vertices 0, 0, 9, 0, and 0, 6. The points P and Q lie on side AB such that AP is equal to PQ is equal to QB. Similarly, the points R and S lie on AC so that AR is equal to RS equals SC. The vertex C is joined to each of the points P and Q in the same way B is joined to R and S. Determine the equation of the line through R and B. Okay, so we will make a basic diagram. So let's label this now. This origin is A, this is P, Q, and this is B. This is C, and then this is S and R. And exactly the way the opening stem describes it, that's what I've connected, those lines that, the vertex C is joined to each of P and Q, and B is joined to R and S, right? Exactly what they're saying. So let's start with part A. Determine the equation of the line through R and B. Okay, so they want you to figure out that equation. All right, that shouldn't be a big problem. C is already given to us as 0, 6, correct? And B is already given to us as 9, 0. And then they tell me these very important equalities, and that allows me to figure out the coordinates for P and for Q and for S and R. That doesn't take that long. Since they're equal, this is going to be 3, 0, and this is going to be 6, 0. Very similarly, this is going to be 0, 2, and this will be 0, 4. So since we have the coordinates for R, which are 0, 2, and the coordinates for B, which are 9, 0, we can easily figure out the equation of the line through those 2 points. So here we go. The equation of any line is y is equal to mx plus b. The m is the slope, which is rise over the run, which in this case would be the 2 minus 0 on the top, 0 minus 9, which is negative 2 over 9. Plug that into here, and we can solve for b. Just substitute any of these points. I'll substitute this guy, and that when I do, it becomes that 2 is equal to b. So therefore the equation is y is equal to minus 2 over 9x plus 2. And however you want to write this, right? You can multiply out by 9 and have 9y is equal to minus 2x plus 18. You can put everything on one side. 9y plus 2x minus 18 is 0. However you want to write it, but all of these forms are correct. Okay, so we're done with part A. Great. Now let's turn our attention to part B. Determine the equation of the line through P and C. Where's P and where's C? Okay, so this is the same story all over again, right? Here's P and here's C. And it's pretty much identical to what I just did. So let's do that. Shouldn't be that hard. Okay. So P and C. Here we go. What is P and what is C? P is 3, 0, and C is 0, 6. So exact same thing. Y is equal to mx plus b. M is the slope, which is rise over the run. So in this case, 0 minus 6 over 3 minus 0, and that is negative 2. Yeah. So that means y is equal to minus 2x plus b. Substitute in one of these points. I'll choose that one. And that means that 6 is equal to b. So therefore my equation is y is equal to minus 2x plus 6. That solves part B. Great. Now we get to part C. Part C is saying the line segments PC and RB. So I guess the two equations that we just did intersect at x. So PC and RB intersect at x. So that means this point here is x. This point right there. So I'll label it x. I guess put the x right there. And the line segments QC and SB. So QC and SB intersect at Y. So that means this point right here, that guy is Y. Okay, so somewhere I've got to put in a Y. I'll just put the Y right there. Okay. And then they're saying, prove that A, X, and Y are on the same line. So they're saying that if you drew a line like that, that A, X, and Y would be on that line. All right. I think I can do that. Shouldn't be a problem. Well, first let's remind ourselves what we already found out. The equation for the line RB was y is equal to minus 2 over 9x plus 2. And the equation for the other line, which, what was it called? PC. Yeah, PC. Politically correct. Political correctness, which is the disease of North America, is the second line, and that is y is equal to minus 2x plus 6. All right, great. So with this, we can easily sort of figure out the intersection point, which is, I guess, between RB and PC. All right, so the equation will allow me to figure out the coordinates of point X. So that's pretty straightforward. Just set these two equal to each other, and we will get minus 2x plus 6 is equal to minus 2 over 9x plus 2. Solving, let's multiply through by 9. We get minus 18x plus 54 is equal to minus 2x plus 18. And when you put everything on one side, you get 36 is equal to 16x. And therefore, x is 9 over 4. And then if you substitute that back into any one of these, you can get the coordinates for y, which is 3 over 2. So this point x, I'll write it over here, has the coordinates 9 over 4 and 3 over 2. Now we have to find the coordinates for y. Well, that is done in pretty much the same way. First, you have to find the equation of SB. Then you have to find the equation of CQ, and then find their intersection point. And since you've already heard me do this a couple times, I won't torture you by doing it again. QC, the equation, I'll just give you the equation, is minus x plus 6. And it's calculated in the exact same way that I did before. And the equation for SB is y is equal to minus 4 over 9x plus 4. And then to find their intersection point, you just set them equal to each other. So minus x plus 6 is equal to minus 4 over 9x plus 4. Solving for this, let's see here, we get, well, multiply through by 9, you get 9x plus 54 is equal to minus 4x plus 36. Solving, we get 18 is equal to 5x. X is equal to 18 over 5. Substitute that back into any one of these, and we'll get y is equal to 12 over 5. So this y coordinate is 18 over 5 and 12 over 5. Okay, great. So now how do you prove that A, X, and Y are on the same line? You prove that in the following way. You have to first get the equation for AX and then show that Y is on that line. If it is, we've proven the question. Okay, so same story. A is 0, 0. X, well, X is 9 over 4. 3 over 2, and when you find the equation, it is equal to, y is equal to 2/3 x, the equation of the line AX. Now, if this point y is on this line, we're done with the question. Let's see. When x is equal to 18 over 5, what is y? Well, this looks to me like 36 over 15. which in lowest terms is 12 over 5, which is exactly what we have there. So that proves, and you can write it out in a sentence, that y is on the line that joins a to x, and that proves part C. In triangle ABC, the points D, E, and F are on sides BC, CA, and AB respectively, such that angle AFE is equal to BFD, angle BDF is equal to CDE, and angle CED is equal to AEF. Prove that angle BDF is equal to BAC. Okay, so obviously we need to label this guy. So AFE, I'll call theta, or whatever you want to call it, right? I mean, it doesn't really matter. Whatever symbols you want to use, I'll just call it theta. And they're saying that's equal to BFD. So where's BFD? BFD is right here. So that's theta also. That takes care of that guy. Then the next one, BDF is equal to CDE. So BDF, I'll call that alpha. And that's equal to CDE. So CDE, there's alpha right there. And then the last one, CED, is equal to AEF. CED, I'll call that gamma. Is this the symbol for gamma? Well, whatever. And this is now gamma, because that's AEF. Okay, so that's basically the labeling of what they've told me in the opening stem. Now I have to prove that BDF is equal to BAC. So where is BDF? BDF is this guy right here, right? So I have to prove that BDF angle is equal to BAC. BAC. Okay, that one I haven't labeled yet, so I'll just call it whatever, beta. So BAC. So I have to prove that alpha is equal to beta. Okay. All right, well, let's see here. I'm going to concentrate on these internal angles here. That will be helpful. So since all the angles about one line are equal to 180, this angle plus those two will be equal to 180. So that means that that angle in there is essentially 180 minus 2 alpha, right? So that one, I'll just call it angle 1. Let's call it angle 1. It's too small for me to write in. Very similarly, this guy, which we can call angle 2, is 180 minus 2 theta. And this little guy in here, which we can call angle 3, is 180 minus 2 gamma. Now, as you know, the sum of all the angles of a triangle add up to 180. So if we add up these three, we should be able to get 180. Okay, so let's do the math here. Let's see here. This gives me 360. And on this side, it'll be 2 theta plus 2 alpha plus 2 gamma. Divide through by 2, and you get theta plus alpha plus gamma. Okay, great. That's a nice relationship. All right, so where do we go from here? Well, we have to start concentrating on this beta, and that's in this triangle right here. But in that triangle, so triangle, what is it, FAE, those angles also add up to 180. So 180 is equal to alpha plus gamma plus beta. Well, these two equations both equal 180, so we can set them equal to each other. So that means that theta plus alpha plus gamma is equal to theta plus gamma plus beta, and that reduces to alpha is equal to beta, which is exactly what I wanted to prove. There you go. And then you can just take it one step further. Therefore, angle BDF is equal to angle BAC. That's it. Part B, if AB is 5 and BC is 8 and CA is 7, determine the length of BD. So we're going to need some space here. Okay. Let's bring it down there. And I think we'll be able to solve this question. So we are going to probably need to use a lot of similar triangles and that kind of stuff. So this is going to be a little bit of algebra here. In the previous part A, we had shown that beta was equal to alpha, right? So if that is the case, that means this up here is the same as alpha. And then since the sum of the angles of any triangle add up to 180, those three add up to 180. And if that's the case, then that also means that if we make the substitution, alpha plus theta plus gamma is 180, and therefore we can conclude that this angle in here must be gamma. And then similarly, that angle in there must be theta. And then once that's established, we can use similar triangles to get relationships between a lot of these sides. So here we go. First is going to be AB over BD is equal to BC over BF. So that's a relationship between the triangles ABC and the triangle BDF, right? Because they're similar because they have the same angles. And the question gives us these side lengths. AB is 5, BC the whole length is 8, and CA the whole length is 7. So from this equation, we can substitute to get 5 over BD is equal to 8 over BF. And therefore, BF over BD is 8 over 5. And we can put that in there. BF over BD is 8 over 5. So that means BF can be written as 8x and BD can be written as 5x. Whatever x is, and we'll probably figure that out later. So I hope you get the hang of that. In a very similar way, we will do another similar triangle. We'll do two more, actually. Now we're going to compare the following triangles. Triangle ABC, the big guy, and triangle CDE. So here we go. In those two, we can do a similar triangles relationship. Comparing the sides, we get AC over DC is equal to BC over CE. And then substituting our numbers, 7 over DC is equal to 8 over CE, and therefore CE over DC is equal to 8 over 7. So we go back and let's label that. So that means if this is 8y, this will be 7y. All right. And then one last one. Now that you're an expert, triangle ABC and triangle AEF. And that gives me the following. AB over AE is equal to AC over AF. So that is 5 over AE is equal to 7 over AF. And that means that 5 over 7 is equal to AE over AF. All right, great. So now we can put in that final one. So that means if AE is 5, let's use 5Z, then AF is 7Z, correct? Okay, great. Now, finally, we can create our equations from that diagram. Let's see. Our equations, this side. That side is going to give me 8x plus 7z is equal to 5, correct? Because that's our whole side length is 5. This over here gives me that 5x plus 7y is equal to 8. And then finally that side gives me that 5z plus 7, or rather 8y I should say, is equal to 7. And there you go. Now you've got 3 equations, 3 variables we can solve. And in the end we have to figure out BD, which is essentially 5x. So once I get the numerical value for x, I can get the value for 5x. All right, 3 equations, 3 variables. Let's solve that now. I'm sure you can do it in any way you want. I'll just isolate for a couple variables here. Let's see what's the best, fastest way. Let's just isolate for z over here. So 7z is equal to 5 minus 8x. So therefore z is equal to 5 minus 8x over 7. Yeah. And then let's see here. Let's add 5x plus 7y. Let's isolate for y in this one. So that means 7y is equal to 8 minus 5x. So y is equal to 8 minus 5x over 7. And then I substitute these two guys into here and here. So 5z is 5 minus 8x over 7 plus 8y. Y is 8 minus 5x over 7. And that all equals 7. Multiply through by 7. And we get 5 times 5, which is 25, minus 40x plus 64 minus 40x is equal to 49. So this looks like 80x, and then 25 plus 64 is 89. 89 minus 49 is 40, and therefore x is a half. Great. And I have to figure out BD, which if I recall was 5x. So that's 5 times a half, which is 5 over 2. There you go. That's the answer. Alphonse and Beryl are playing a game, starting with the geometric shape shown in Figure 1. Alphonse begins the game by cutting the original shape into 2 pieces along one of the lines. He then passes the piece containing the black triangle to Beryl and discards the other piece. Beryl repeats these steps with the piece she receives, that is to say, she cuts along the length of a line, passes the piece containing the black triangle back to Alphonse, and discards the other piece. This process continues with the winner being the player who, at the beginning of his or her turn, receives only the black triangle. Show with justification that there is always a winning strategy for Beryl. All right, so how do we do that? Well, there's 2 possible ways that we can have Beryl win. Winning strategy for Beryl. So let's say we start off with that original shape, which is below, and it looks like this, right? You got this sort of scenario like that, not drawn to scale, but you get the idea. Now what they're saying is that you have to cut this along one of the existing lines, so either there, right, or here, like that. So here's the strategy. Who goes first here? Alphonse begins the game, right? So Alphonse goes first. So A goes first. So the first thing, the strategy is that you have to get Alphonse to remove 2 of these. So once that cut is made, removes 2 triangles. And what you're left with is sort of this kind of scenario. Like that, where these 2 have been cut out. So you're left with that. Then Beryl, it's her turn. So she removes 1 triangle. So she will remove this guy right here. And when she does, what you're left with is just the black one, and then the one attached to it like that. And then Alphonse has no choice but to remove the last triangle, which is this guy, and then that leaves this just the black square. And if you read the question, this process continues with the winner being who at the beginning of his or her turn receives only the black square or black triangle. So the next person to go is Beryl, correct? And because the next person Beryl receives the black triangle, that means she wins. So that's basically the strategy for Beryl to win. That's strategy number 1. All right, great. So I think there's one more strategy, and let's talk about the next strategy. So strategy number 2. Again, Alphonse goes first, so he will remove, or we will say, well, what if he removes only one triangle? This is the other scenario, right? So he removes just this guy. Okay, so if that's the case, what you're left with is this scenario where you've got that kind of a shape where this is the black triangle. Correct? Okay. So then the next step, Beryl's turn, she will remove 2 triangles. So she will cut off those 2 guys. And then if that's the case, you're left with this shape where this is the black triangle. And then Alphonse has no choice but to remove just the final one, that one triangle, this one. And when that is removed, it leaves just the black triangle. Then it's Beryl's turn. And since Beryl receives that black triangle, she wins, according to the definition of the game in that opening stem. So that's basically the strategy. And regardless of what Alfonso does, Beryl can win by making the appropriate cuts. All right, so now part 2, part B, whatever. Alphonse and Beryl now play a game with the same rules as in A, except this time they use a shape in figure 2, and Beryl goes first. As in A, cuts may only be made along the whole length of a line in the figure. Is there a strategy that Beryl can use to be guaranteed that she will win? Okay. So a little bit different this time, right? Beryl goes first. Now, if Beryl goes first, our strategy basically is to make this figure 2, reduce figure 2, or cut it out and cut it in such a way to make it look like figure 1. And then once you get it to be like figure 1, you use the strategy that I just described in part A. Then proceed as in 3A. 3A was part A of this question. And of course, you have to make Alphonse make the first cut at that point. And have Alphonse make the first cut. All right, so that's how we're going to begin. Now, before we begin, we have to label this, otherwise it's going to be way too confusing. So this point right here, I will call 1, and the direction of the arrow represents the cut. So it's like this, that's the cut. Similarly, this point here, I will call point 2, and this arrow represents the direction of the cut that is to be made. Similarly, 3 will be this point, and the cut will again go in this direction. This point will be 4. Hold on, here, I've got to write it in a way that I draw the arrows. That's 4. The cut will be made like that. This is 5. The cut is in that direction. This is 6. Cut in that direction. And then let's see here. This will be 7. This will be 8. And this will be 9. All right. So here we go. The first way is as follows. Barrel goes first, right? So barrel cuts 1. So that means the cut is like this. Okay. So then it's Alphonse's turn. He cuts, say, 2. So now he cuts that. Then barrel will cut 3. So once that cut is made, that cut is made, and that cut is made, we have reduced the shape to just looking like figure 1. Correct? And then the next turn, it's A's turn, and he will receive essentially figure 1. And with the same strategy, in 3A, barrel will win. So as you can see, this scenario makes barrel win. Now, because of the symmetry of this diagram, this 2 and 3, if you substituted, instead of 2 and 3, cuts 8 and 9, or if you substituted cuts 5 and 6, it would end up with the same result. And you can do that on your own because it's essentially a symmetrical diagram. All right, so that is the first strategy. The next strategy is a slightly different scenario. What if B, that barrel goes first, instead of cutting 1, she cuts slightly different order, I guess. So she starts off cutting 1, but then what about A? What if A cuts 4? Right? Because this scenario here already takes care of a lot. We've taken care of 2. So let me just circle those. 2 is taken care of, like if A. And it also takes care of 8. And also takes care of 5. So we have to now concentrate on the other numbers. So let's concentrate on 4. Let's say barrel cuts 1 and then A cuts 4. So we've made this cut and then 4 would make this cut, right? So now we can proceed with barrel. She will cut 7. And then now is when Alphonse has a lot of choices. Got anywhere of 2, 3, 5, 6, 8, or 9. Right? Because we've cut 1, we've cut 4, we've cut 7. So now 2, 3, 5, 6, 8, and 9 are empty. So let's figure out a scenario to make sure that barrel wins. At this point, let's say that we have to give an example here. So I'll say that let's say that the cut that A did was 2. So let's show it on the diagram here. We have 1 out, 1 cut, 4 was cut, 7 was cut, and then now A cuts 2. In order for barrel to make this shape look like figure 1, she would have to cut 3. Correct? So that's what we will make barrel do. So barrel cuts 3. The point I have to make here is that whatever happens here, barrel has to make the appropriate cut to make it look like figure 1. And there's always going to be one possibility. So I showed you 2 as a cut there and then 3 as a cut there. So 1, 4, and 7 were these 3 steps, right? But let's say instead of cut 2, A decides to cut 5, like that. Well, Beryl would then have to cut 6 in order to make the remaining shape look like figure 1. So the point is that whatever A decides to do at this step right here, Beryl has an option in her step here to make the figure look like figure 1. And then, as before, then it's Alphonse's turn, A's turn, and he receives basically figure 1, a shape that looks exactly like figure 1, and then you just continue with the strategy described in 3A, and then Beryl will win. And that's it. And I encourage you to kind of go through this to convince yourself of the symmetry, that you don't have to go through every single one, because these two scenarios, this one here and this one here, describe pretty much every scenario, because every other scenario will end up to be the same because of the symmetry of the diagram. A sequence T1, T2, T3 until Tn of n terms is defined as follows. T1 is 1, T2 is 4, and Tk is equal to Tk minus 1 plus Tk minus 2, for k equals 3 to n. Let T be the set of all terms in the sequence, that is T is equal to T1, T2, and so on. How many positive integers can be expressed as the sum of exactly 2 distinct elements of the set T? So the first step, I think the easiest way is to sort of write out the numbers. So using this recursive formula, I can get the first few steps, first few terms. T1 they already gave me is 4, T1 is 1, T2 is 4. The next one, which would be T3, is essentially just the sum of the previous 2. So that's going to be 5, right? 1 plus 4. The next term, which is T4, is essentially the sum of the previous 2 terms, which is 4 plus 5, so 9. And then so on. This one will be 14, that's T5, and then T6 will be 23, and then so on. It just keeps on going like that. So this was T1, this was T2, T3, T4, T5, and T6. I think that should be enough to describe what's going on and then prove our question. So what they're saying is that if you take any 2 of these terms and add them, the sum of exactly 2 distinct elements, what possible sums do you get? How many of them? So for example, if I took 4 and 9 and added them, I get 13, right? So 13 is one possible sum. If I added 5 and 23, I would get 28. That's another possible sum. They're saying if this keeps on going until Tn, which is some number, I don't know what it is, how many possible sums like this can you get? Okay, well, that isn't that difficult, because think about it. How many terms are there in this whole set? Well, there's n terms. And to make a sum of 2 distinct elements, you have to choose 2, correct? So from n terms, you have to choose 2. So n choose 2 is the number of pairs, correct? And I think that each pair will produce a unique sum. A unique sum, or another way of writing it, is a different integer. Different integer. Now, if that's the case, I'm done with my question. But here's the thing. I have to show that all of these sums are unique, that no 2 sums are the same. So for example, if I chose 2 terms, let's say, whatever, right, TA and TB, and I added them, I have to show that no 2 terms can be added to equal the same integer. So if I chose 2 other terms, TA TC plus TD, that no two sums would be the same. So essentially what I'm really trying to show is that can any two pairs produce the same integer sum? Can any two pairs produce the same integer sum? If the answer is no, then the answer to this question is just a simple n choose 2. If the answer is yes, then I have to subtract those from this guy, because those ones would be doubles basically, right? All right, so here we go. I'm going to choose 4 terms: TA, TB, TC, and TD. And they're all distinct. They're all different. So none of these 4 are the same. And then you put this sort of in order and say this one is the largest in terms of its numerical value. TD is the largest. Okay. So now I have to figure out, can TA plus TB equal TC plus TD? Yes or no? I don't know. We have to figure this out. And throughout this, I will use some of these numbers, otherwise it'll become a little too abstract. So let's see here. TD I had called the largest, right? Okay. Now from our recursive formula that's given in the question right there, we can conclude that TD is equal to TD minus 1 plus TD minus 2, right? That's just directly from the question. Now, we know that, let's say this is TD, right? I gotta give some numerical values, otherwise it'll be a little too abstract. Let's say TD was 23. Well, according to my nice little set of numbers, this is 14 and this is 9. Now, if I talk about the other guys, TA and TB, say TA plus TB, well, TA and TB are obviously distinct. They're different from TD. So they obviously are not going to be 23, but they could be, say, 14, and they could be 9, right? So that means that this TD minus 1 plus TD minus 2, which is equal to TD, this whole thing, could be equal to TA plus TB, right? If I chose my numbers as 9 and 14, then if you add those two guys, it could be equal to TD. That is possible. But so keep that in mind. But what if I chose different numbers for TA and TB? Let's say I chose TB, I don't know, whatever, 14, but then for TA I chose it to be 5. Well, in that case, the sum is 19, and that's less than 23. So that means this is now going to be a greater than sign. So if you combine these two, I've concluded that TD is always going to be greater than or equal to TA plus TB. And I hope when I put in some numbers, it became clear. I just put in those numbers up there. Okay, so this sort of inequality or equality, whatever it's called, I hope is clear. All right. So if that is true, then think about what happens next. Let's use the first guy, which is TD is equal to TA plus TB, this scenario. If it is equal, and then you add on a TC, like that, then that means that TC plus TD will be greater than TA plus TB, because TC is always going to be some positive number. And therefore, if this is greater than that, it means that it is not equal. So that means, conclusion, therefore, TC plus TD is not equal to TA plus TB because I've just shown that it's greater than. Okay, great. Now we have to look at the scenario where TD is greater than TA plus TB, which was this scenario right here. If that's the case, if I add on a TC to this side, then again, it continues to be greater than, correct? And again, we've sort of shown the same thing, that therefore TC plus TD cannot be equal to TA plus TB. So in both scenarios, we showed that this is not possible. We cannot have two sums that are equal. And therefore, that means that all the sums are unique. So my original question, each pair produce a unique sum? Can any two pairs produce the same integer sum? And the answer is no. So therefore, the answer to this question is just n choose 2, because all of those pairs will produce a unique sum, a different integer. Part B, how many positive integers can be expressed as the sum of exactly 3 distinct elements of the set T? All right, so now they have decided to go and talk about 3 instead of 2. Okay, so now we are told we've got TA, TB, and TC, and then they're adding them, and then same kind of story. How many different unique sets can you get? Well, just as before, I'm going to use the same numbers, right? If you remember, the set was 1, 4, 5, 9, 14, 23, and then it just kind of keeps on going, right? Dot, dot, dot. So they're saying that if you take any 3 of these and add them, you will get an integer. How many different integers can you get? How many unique sums? So how many unique triplet sums, I guess? Well, let's see. As before, the total number of terms in this set is n, right? And we're selecting 3 this time. So n choose 3. This is the total. But my question, just as before, is that are there any that are the same? Because if they are, we have to then subtract those from this guy. So basically what I'm asking, just like before, is can you get the same sum if you use 3 different terms? So if TA plus TB plus TC are used, can it equal 3 other terms, which I guess we can use D, TE, and TF, like that? If that is yes, if the answer to that is yes, then we have to subtract those guys from this n choose 3. Does that make sense? So here we go. Well, let's see here. I think just based on the fact that a lot of these guys are sums of each other, we can do this. So let's say I made this guy 23. It's the largest. And then I'll make this 9 and this 14, which is basically 9 plus 14 is 23. And then if I made this one 5, and then this one 1 and 4, which is essentially the sum, then there you go. I've just made it. 9 plus 14 plus 5 is 28. 1 plus 4 plus 23 is 28. So yes, of course, it seems pretty obvious that this can be done with 3 terms on this side and 3 terms on this side. So my question now is, how many of these scenarios can we have? Okay, so this is where you really have to sort of pay attention here. So let's talk about this. Concentrating on TF. TF. How many TFs can I have? Well, TF is the largest of these 6, correct? So TF, if this was T1, this was T2, this was T3, this was T4, this was T5, and this was T6, correct? This 23. The F has to be at least 6, correct? It can't be 5 or 4 because we've got 6 distinct numbers, and TF is the largest of the 6, so it's got to be at least 6. It could be 7, 8, 9, but it's got to be at least 6. And then obviously, since there's n terms in that whole set, F has got to be less than or equal to n. Okay? So that's sort of the definition of what F is. What about TC? This guy right here. Well, if this is TF right here, in order for this to work, we designated TA and TB, notice, to be 9 and 14. So these immediately preceding two terms. So the largest TC can be is the next term, which means that C, the largest it can be, is F minus 3, which in this case was 6 minus 3, which is 3, which makes sense. It matches. I hope that makes sense. And then the smallest that it can be, remember, we can't use the first term or the second term. We have to use at least the third term in this particular example. So the smallest that C can be is 3. All right, so there we go. That's the definition for F and C. So that means for any given F, for any given F, we have how many choices for C? How many choices for C? Well, essentially what I'm asking is, how many numbers is that? Well, in our case, F, we had chosen it to be 6, right? So we have to figure out what is the scenario if we just have this. How many numbers are there from 3 to F minus 3 inclusive? Well, the only numbers we don't have are 1 and 2. So basically, it's F minus 3 minus 2, meaning this represents the 1 and the 2. We can't have F1 or F2. We start with we can't have T1 and T2. We start with T3. So F minus 3 minus 2 is F minus 5. Correct? So let me just give you an example. Let's say we had F equal to 12. Correct? That means F minus 3 is 9. So how many numbers are there between 3 and 9 inclusive? Well, it looks to me like it's 9 minus 2, which is 7. So that's basically how you'd get 7, would be 12 minus 5. So hopefully that made sense. Okay, so now the total number of choices, F minus 5, but F can be anything from 6 to n, so it's a summation. The total number of choices is the sum of this F minus 5 for F going from 6 to n, according to what is written there. So this looks like to me, when F is 6, this becomes 1. When F is 7, this becomes 2. When F is 8, this becomes 3, ... And it just keeps going until you get to n minus 5. And you guys remember that nice formula that if you have the sum of consecutive numbers 1 plus 2 plus 3 ... until n, the sum is equal to n times n plus 1 over 2. So you use the same formula here. In this case, it would be n minus 5 times n minus 5 plus 1 all over 2. And that looks to me like n minus 5 times n minus 4 all over 2. This represents what? This represents the number of triplet sums that are the same. Correct? So, same triplet sums. So this represents this scenario. And what we need to do is subtract that from the total, which is here. So that means the number of unique triplet sums, unique triplet sums, is equal to the total number, which is n choose 3, minus this guy right here that I just got, which is n minus 5 times n minus 4 all over 2. And this is the answer to the question.